Okay. Hello everyone, my name is Chris, and today I'll be talking, as you mentioned, about decoupling data layouts from bounding volume hierarchies. This is work done in collaboration with my colleague, AJ Root, and my esteemed advisor, Fred Kjolstad. Okay, so BVHs are really indexes for speeding up spatial queries. Here we present a very simple scene consisting of 6 triangles, but notably these can range from millions to billions of primitives. And we have the following query we might want to speed up. Notice the ray in the lower left corner, and the question we might ask is, which triangles in the scene does the ray intersect? And there's a couple ways we can do this. Perhaps we store these triangles in a list naively, and we perform a ray triangle intersection test for each of these. But this approach has a drawback. No matter what the scene is, we always have to perform this ray triangle intersection test, which is relatively expensive for every triangle in the scene. And so one alternative approach to this is using an acceleration structure aptly named the bounding volume hierarchy, which recursively partitions objects in a scene and often asymptotically reduces the amount of work a spatial query must perform. This is represented as a tree data structure where each node bounds or envelops its children. And so we can perform the same queries we did before. And so we start at the bounding volume named A. And we ask the question, does the ray intersect A? The answer clearly here is yes, so we'll recurse into each of its children. We'll start with the ray children, the bounding volume C. Here we see that clearly the ray does not intersect C, so actually we can skip any work within C, and we don't have to recurse to D or E at all. We continue this process until we get the same exact answer as before, but in a much more work-efficient manner. And so what we've seen is that, in fact, these BVHs are used in numerous domains for many different types of spatial queries. This includes ray tracing in hydrodynamics, closest point query for robotics, collision detection used in physical simulation, and neighbor search used in molecular simulation. And what we've also seen is that these physical representations of BVHs is quite extensive. So here we've provided the components to describe a single node of a BVH. Namely, we need some way to describe the leaf and its fields, the interior nodes in its fields, a way to discriminate these, and finally the bounding volume, which here we've chosen, we made a choice of bounding volume, namely an axis-aligned bounding box, or AABV. And so one physical layout we might choose is the following, where we have a struct called node, and first we store a tag as 8 bits. We then store the axis-aligned bounding box, and finally we store the union of the leaf and interior node. Where in the case of the leaf node, we have these wasted bits, or wasted space rather, because the leaf node is much smaller in size than the interior node. We can also choose the following representation, where instead we store the axis-aligned bounding box first, and we store a single bit to represent the tag, because clearly there are only 2 different cases we have to distinguish. And so what I claim is there's many works that have actually done a really good job of describing these bit-precise level layouts to include bit stealing made legal for algebraic data types, and also Dargent for these records and sum types. And what we're actually interested in is not only these intranode or per-node optimizations, but also internode optimizations, or optimizations across collections of nodes. And so here we have a very naive pointer-based layout, where each interior node contains a machine pointer to its left and right children. And this is really nice for data structures that are often readily mutated and shared. However, what we've seen is that these BVHs remain relatively static, and thus there lies a lot of performance in thinking about more read-friendly data layouts. And so we can consider the following tree laid out in a pre-order traversal in a single contiguous array. And this gives us better locality first. And second, what we get is that because this is laid out in pre-order traversal, we don't actually just store an explicit index to the left child. This is known implicitly. It lives directly after the parent. We can also consider this alternative layout, where we now store fields in separate arrays, which really cater to these highly vectorized machines such as GPUs. And lastly, as I mentioned earlier, we have this wasted space in the leaf case, and we might consider a more space-efficient layout such as the following. Here we store interior nodes and leaf nodes in separate arrays, and we actually encode in the reference type which array to actually look up into. And when actually implementing a BVH, what we're trying to do is minimize 2 objectives. This is obviously the runtime performance of the spatial query. That's the entire point of BVHs. But we also want to minimize the memory footprint of the BVH itself as well. And the reason for this is that these can be run on these more memory-constrained architectures such as mobile devices. And so what this gives us is not a single optimal layout, but rather a Pareto frontier of layouts to explore. And so, for instance, a Pareto-optimal layout, the objectives of what I claim here is that the objectives are dependent on 3 factors. This includes the algorithm, so collision detection or neighbor search perhaps. It includes, obviously, the machine you're running it on. And so, the Pareto-optimal layout for an x86 CPU with SIMD instructions is going to look much different than one for a GPU. And finally, it's going to depend on the characteristics of your input data. A sparse and dense scene will likely have very different ideal layouts. And perhaps, if you're doing ray tracing, whether your rays are coherent or incoherent are also going to be important in choosing a Pareto-optimal layout. And so when we look at prior work that optimizes these BVHs, well, we notice that each prior work is really focused on one point in this design space. So we can concretely consider work from folks behind Embry, which is an industry-level graphics rendering library. And they have this paper dedicated solely to optimizing ray tracing on x86 for densely packed hair. And here are 2 other works that are really focused on entirely different points or evaluation contexts. And if this still isn't convincing, we cite an entire collection of papers that emphasize the importance of optimizing the physical layouts of BVHs for different points in this design space. And so obviously one sub-goal of this work is really to design a language that can express many of these layout optimizations. But more importantly, what we want to do is get away from this traditional approach of every time you need to explore a new physical layout, you have to write the logical specification in the algorithm over and over again. And so we propose this decoupling, where one time the domain expert writes an algebraic data type for the BVH, as well as a set of traversal algorithms, and separately the performance engineer can provide different physical specifications to explore perhaps different evaluation contexts or different points on the Pareto frontier. Okay, and so we provide a very high-level system overview of what our work looks like. And so first, the application developer, as I mentioned earlier, writes a tree traversal algorithm and some algebraic data type. Separately, the performance engineer or perhaps an auto-scheduler will write the physical layout. These are passed into our compiler, where we specialize the physical layout for the given algorithm code and then perform some domain-specific optimizations. And finally, we generate code for 3 different targets: x86, NVIDIA, and ARM. And I think one of the really cool parts about this work is actually every tree traversal algorithm we use in this paper was automatically generated from Bonsai using high-level set queries. And if you're interested in this or in mechanization of pruning tree traversals, you should go see AJ's talk on Friday at 4:30 p.m. Okay, so now we'll talk about each of these components in a little bit more detail. So first, we need a way to actually specify a logical interface. And so we have this type BVH. And a key insight of this work is when we're writing algorithms for spatial queries, we don't actually have to make any assumptions about the physical representation of the BVH. So here we specify a very simple ADT or BVH as an ADT. And so we have the type AABB, which is represented as 2 points in space, the lower and upper corners. And then we have the BVH, which is a sum type, where either we have an interior node containing the bounding box, the left and right child, or we have a leaf node which also contains the bounding box, some number of primitives n, and the primitives themselves. We can then write algorithms with respect to this algebraic data type. Here we have a very simple closest hit ray tracing algorithm with some pruning in addition to it. And again, we're making no assumptions about how this BVH, how this algebraic data type is laid out in memory. Okay. The next part of this talk, we'll talk about specifying the physical interface of the BVH implementation, focusing on our layout language. And so to introduce the constructs of the layout language, we'll build the layout from ground up. And here we begin by defining a layout called linear BVH, which currently only contains an array of triangles over which we'll construct the BVH nodes. And so the first construct we'll discuss is a group, and we'll do this by showing an example. Here we have a very simple group called G1 that has exactly 4 elements, and it's indexed by the value I. And each element in this group contains a field called A of type F32, followed by a field called B of type I8. And so when we look at I equals 0, we point to the first A and B. I equals 1 points to the second A and B, so on and so forth. We can also do the structural arrays optimization, where we have 2 different groups with a single field, but share the same indexing value I. And finally, we can compose these groups to do more advanced optimizations, such as array of structural arrays. And so in our, returning to our original layout, what we're doing here is replacing two fields in our group, namely the bounding box and also the value n, which represents the number of triangles that this node contains. Okay, so the next construct we'll talk about is split. And simply put, a split is just a way to do safe union types. And I should say this is highly inspired by prior work, namely bit stealing made legal. And what we're saying here is that if n, the number of triangles, is greater than 0, this is a leaf node. And otherwise, if it's equal to 0, this is an interior node. And this is simply an invariant of BVHs. And the nice part about this is now we don't have to explicitly store any kind of discriminant or tag. We then place some fields in each of the cases of our split, but additionally we have this notion of derived fields. So derived fields don't actually store any bits. This is just a way to compute some information on the fly. And so the canonical example, as I had mentioned earlier, is that if we know this array is stored in pre-order traversal, left to right, we don't actually have to store an index, an explicit index to the left child. We know it always lives directly after the parent. And finally, we had 16 bits of padding so that every element in our group nodes is 4-byte aligned. And interesting, I think the interesting thing here is we've actually built a layout that is modulo a few small changes that we skipped for brevity. The one that's used in the physically based rendering textbook, which has been shown by the authors to be sufficient to render some of the largest scenes publicly available from Disney. Okay. What our claim is that, with a couple more constructors or operations that we don't show in this talk but are in our paper, this is actually sufficient to express many advanced layout optimizations used in real BVH applications. This includes things like bounding volume quantization, which trades off a more compact layout for less work efficiency during traversal, but is still functionally equivalent in the world of spatial queries. This includes sum of arrays, as depicted earlier, which is a way to more compactly store some types where each injection may have disparate sizes. And here we're seeing a trade-off of space for additional compute at runtime. And finally, we provide a way to forego storing redundant information that might be shared between a parent and its children, thus allowing optimizations such as shared slab, where only a subset of the slabs of a bounding volume need to be stored for each child. Okay. The final component that we're going to talk about today is actually, how do we automatically specialize the layout for the given traversal algorithm? And so we do this through a process that we denote as destructor specialization. And so on the left-hand side here, we have a subset of the closest hit ray tracing algorithm. And the question is, how do we actually specialize accessing the field called right for the interior node, which represents the right child? And on the right-hand side, we provide the layout. And so we do this through a very simple pathfinding algorithm, where we start off with a base case, which is the name of the layout, and we proceed until we actually reach the field called right in the layout. And so first we jump to the group called nodes, accessed by the value I. We then jump through the split to the interior case, because the right lives in that case. And finally we access a field called right as required. We do this for every different field that's actually used in the algorithm. And finally, we apply some domain-specific and common compiler optimizations such as DC and CSE, and we found that we get better performance than general-purpose compilers such as Clang because we can make some stronger assumptions we can make some stronger assumptions in our higher-level IR. Okay. Additionally, we also perform constructor specialization. I think that the main takeaway here is that not all layout optimizations we want to do are invertible. And also, we need some way to specialize a constructor code, which maps like a BVH from a naive layout to the specialized layout. I think this is really interesting too, and you should see the paper for more details or come talk to me after this. Okay, and so to demonstrate there's no overhead with our techniques, we compare against two state-of-the-art libraries. The first one is the fastest closest point in the West, where we compare the running time of closest point query across a number of different scenes. And the second one is flexible collision library, or FCL, and we compare in a similar manner for collision detection, but this time for a number of different layouts. And the only claim I'm making here is we're about parity in both cases, and the reason for this is honestly we just have a monomorphizing compiler, and thus we have no runtime overhead because of our work. Okay, and lastly, to show the utility of our work, we actually performed this large design space exploration for closest hit ray tracing algorithms. And so, again, the point we're trying to make here is we're not trying to explore a single optimal layout, but rather this Pareto frontier, minimizing the runtime of closest hit ray tracing, and also the memory footprint of the BVH we're using. And so we do this for 19 different layouts. This consists of realizing prior state-of-the-art optimizations, but also some minute changes, such as changing the alignment of specific groups elements. We do this across 7 different scenes, which ranges in sizes from thousands of triangles to tens of millions of triangles, 2 different ray distributions, both incoherent and coherent rays, and finally 3 different machines, x86 NVIDIA GPUs and ARM CPUs. And what we show is that indeed, empirically we show that Pareto-optimal layouts are algorithm, machine, and data specific, and you should see the paper for details that actually back this up. And hopefully this is surprising no one. Okay, and I think, again, another really cool part about this work is we are able to rapidly explore novel layouts. So here we combine optimization techniques from 3 different works. Namely, we have the implicit indexing and bit sealing from the linear BVH that I showed earlier. We use a SnapGrid X10 quantization technique, or bounding volume quantization technique, from a paper that's optimizing molecular simulations. And we use this dequantization scheme from the Embry folks who had a paper on compressing leaf-based bounding volume hierarchies. And this gives us a novel layout that we denote as PBRTQ16. And perhaps we can look at a single point in this evaluation context, namely Lucy, which is 28 million triangles, run on x86, and using coherent or primary rays. And clearly, PBRTQ16 is Pareto on the Pareto frontier. And interestingly, it's about 5 times faster than the most space-efficient layout that we were exploring previously. And also about 2 times, uses about 2 times less memory than the fastest layout we were exploring previously. But most importantly, what we saw is that PBRTQ16 is Pareto-optimal in 35 of the 42 different evaluation contexts we were looking at. And so I think the main takeaway that we're trying to get at here is that physical layouts are important for these acceleration structures when seeking peak performance. And we believe this decoupling of data layout optimizations is crucial for making performance engineering as productive as possible. Thank you.
Thank you. Yeah, we have 3 minutes for our question now.
Hey.
Hi, thank you for the talk.
Uh-huh.
So I see the sort of set of expressible spatial layouts. I was wondering a little bit more about the algorithmic language and your ability to express some of the other Embry optimizations, like they do packet tracing, and they'll swap back and forth. Like, what are your thoughts on those sorts of constraints?
My thoughts are the algorithm side is very important too, and actually my colleague AJ Root is working on exactly this. So you should talk to AJ Root after this. So AJ Root, this is originally a work done by AJ Root that I've kind of built upon, and he has this entire system for optimizing these spatial query programs that really is combining both data layout optimizations and what we call scheduling, which includes things like packet tracing. And I think what is really cool about this is we're composing both of these together. So yeah, talk to AJ Root.
Thank you.
Very nice work. I'm curious of whether this has application to specifying file formats and network formats.
Yes. So we have 2 different approaches after this paper. One, we either convince everybody that BVHs are the only important data structures and everything should use BVHs. I've failed to do that so far. The second option is to generalize this to all algebraic data types. And we are currently doing this right now to include file formats and network-like formats. But anything that can be represented as an algebraic data type hopefully can benefit from stuff like this.
Any more questions? All right, let's thank our speaker again.